Hello everyone. As I promised in class, I go over example 3 from section 3.5 with the guidelines from our book. Let's see what is that example first. The question is example 3, we will sketch this function let fx equals to cosine x over 2 plus sine x. You know what? Let me make sure that's the question. That's right. That's the question. Okay. We will follow the guidelines from our textbook, which in my opinion already makes sense because the first part, part 1, is basically analysis on fx, right? Where we find the domain, and then the intercept, x-intercept and y-intercepts, and then symmetry or the period. In this case, we know we have a period because it's trigonometric, right? Okay, and then part D, we look for the asymptotes. And then the second part, we do analysis on f prime x, so we need to know how to do the derivative, right? Okay, and then using that derivative, we will work on the interval of increase, interval of decrease, and the local max, local mean, after that we go on to the second derivative, the third part, and then do analysis on concave up, concave down, and inflection point. Then after that we do the sketch. Okay, now let's start with this function, the first part. What is the domain? The domain will be, the domain for the numerator is all real numbers, right, for cosine. For the denominator, we need to make sure it's not 0, but 2 plus sine x will be at least 2 plus negative 1, because the range of sine x is at least negative 1. Okay, so this is at least 1, right? In other words, the denominator can never be 0. In this case, therefore, the domain will be all real numbers. Okay, part B, how about the intercept? The y-intercept, we set the x equals to 0. That would be cosine 0 over 2 plus sine 0. Cosine 0 is 1. Sine 0 is 0, so this is 1/2. The y-intercept is 0, 1/2. Let me give myself some space here. Oops, no. How about the x-intercept? Notice that this has a period, right? The x-intercept is when fx equals to 0, but fx equals to 0 if the numerator is 0. Now cosine x is 0 when x is pi over 2 plus any constant multiple of pi, where k is an integer. Okay, so the x-intercepts will be pi over 2 comma 0, 3 pi over 2 comma 0, and a lot more. Maybe, you know what, I write it in more general term. My bad. let me move this a bit to the right so that I have more space. And then x-intercept is pi over 2 plus k pi comma 0. Okay, part C. How about symmetry? Let's check what is f negative x. This is to check y-axis symmetry or origin symmetry, right? Cosine negative x over 2 plus sine negative x. This is equal to cosine negative is cosine positive because cosine is an even function. However, sine is an odd function. So sine negative x is negative sine x. Now, this is clearly not equals to fx. Okay, also not equals to f negative negative fx. Okay, so the graph of fx, I would just say fx. Fx has no y-axis nor origin symmetry. Okay, however, since the function depends on sine x and cosine x, right? Sine x and cosine x have period of 2 pi. It repeats every 2 pi. We will consider the domain x from 0 to 2 pi only. And then after that, when we sketch that, we will copy paste. Okay, we'll copy paste every 2 pi. We copy paste whatever we have in this first period from 0 to 2 pi. Part D, asymptotes. Because the domain is from negative infinity to infinity, let's check horizontal asymptote if we have any. I don't think so though. Limit x approaching infinity. Not supposed to, huh? We don't have asymptotes because it is periodical, right? Okay, it's periodical. But let's try anyway, you know. So cosine x over 2 plus sine x. Yeah, because of the period, this becomes does not exist. Right? Yeah, because the top one oscillates between -1 and 1, but the denominator oscillates between 1 to 3. Okay? In fact, it is true even when we deal with negative infinity. Okay, let me just limit x goes to positive negative infinity does not exist. Okay, vertical asymptotes. Well, since the domain is all real numbers, then there will be no vertical asymptote. Okay, since the domain is all real. Now, at this point, we can say the following, that we will be working at the domain will be from 0 to 2 pi only. And whatever we have there later on, we will copy paste. Okay, so let's say this is 0 1/2, that's the y-intercept, right? Okay, and the x-intercept pi, so this is pi over 2 and 3 pi over 2. We have these 2 points here. What that looks like, I don't know. Okay, how to connect this later on, what the graph look like, I don't know. Maybe it may look like this. I don't know. Maybe. Is it true? Okay, we don't know yet. But at least we know that it must pass this y-intercept and these two x-intercepts here. Okay. Oh, also due to the period, then at 2 pi it will be 0,1/2 again, right? So this is 2 pi, 1/2. Okay. But that's what we have right now. Let's go on with the use of the first derivative. So second part, let's do, so this is the first part here, right? Where we analyze the function. Second part, we do the first derivative. First derivative, what is the function first? Let me copy the function first. Fx equals to cosine x over 2 plus sine x. So f prime x is equal to the derivative of the numerator, let me write it this way for now, times the denominator minus the numerator times the derivative of the denominator over the square of the denominator. Oh, we already observed the denominator cannot be 0 earlier, right? Yeah, here we did the domain. So we will not have a critical number due to the denominator being 0. Okay, we'll take care of that later on, but at least we are aware that that knowledge will be very helpful. So negative sine x for the derivative of cosine x. You know what? Let me enlarge this a little bit so that you can see with me. Then 2 plus sine x minus cosine x times the derivative of 2 plus sine x is another cosine x. Over 2 plus 2 sine x being squared. So on the numerator, I have negative 2 sine x minus sine squared x minus cosine squared x. Oh, you know what? That becomes negative 1, right? 2 plus, who wrote that 2 here? It should not be any 2 there. Okay, plus sine x being squared. Simplify further, this is negative 2 sine x minus 1 over 2 plus sine x squared. Let me factor the negative. So I get negative of 1 plus 2 sine x over 2 plus sine x being squared. Okay, now then from here we find those important numbers. I usually call that critical numbers, but in the sense that what are the numbers that make the numerator become 0 and the denominator become 0. Okay, f prime x equals to 0 when the numerator is 0. Okay, so sine x is equals to negative 1/2. So x will be in quadrant 3, quadrant 3. So that's 7 pi over 6. And quadrant 4, that will be 11 pi over 6. Now remember, it's supposed to be plus 2 pi, 2k pi, right? But we decided earlier that we will be working on interval from 0 to 2 pi only, and then we copy paste later on. Okay, on the other hand, the f prime x is undefined when 2 plus sine x equals to 0, but we never have that case because that implies sine x is equals to -2, which is not applied, right? Because the range of sine x is, because sine x is between -1 and 1, right? So can never be -2. Okay, now using that, then we go to part E, the sine graph for of that f prime x. So we have the domain. The domain is only, we will consider only from 0 to 2 pi, right? The domain is all real numbers, that's true. But we will operate on 0 to 2 pi only. And then, I'm sorry, this is pi, this is 3 pi over 2, 7 pi over 6 is here approximately. And according to what we see, that it will make the f prime x equals to 0. And 11 pi over 6. That will also make it 0. Now then, going back to that f prime x, when x is, let's say pi, when x is pi, when I do testing point, okay, so f prime pi is equals to negative of 1 plus 2 sine pi, that's 0, over 2 plus 0 squared. Oh, that's negative, huh? So in this region, the slope is negative. It is decreasing down to 7 pi over 6. And then let me do testing point at 3 pi over 2. Negative 1 plus sine 3 pi over 2. That's a 2. Sine 3 pi over 2, that's negative 1 over 2 plus sine 3 pi over 2 is negative 1. That's squared. So that will be negative of, on the top I get 1 minus 2 over 1 squared. That's positive, huh? Positive 1 to be more precise, right? That's positive. So the slope is positive between 7 pi over 6 to 11 pi over 6. Now you will see later on when I try the 2 pi, I will get negative 1 plus 0 over 2 plus 0 squared again, which is negative. Okay, so this part here, this is negative. Okay, with that said, then we see f(x) is increasing on the interval from 0 to 7 pi over 6 union 11 pi over 6 to 2 pi. The function is decreasing because the slope is negative between 7 pi over 6 to 11 pi over 6. With that said, then we can also see we have, well, the slope is going down here, the slope is going down here, and then later on go up here, so it will be local minimum at 7 pi over 6. Local minimum at x equals 7 pi over 6, and the local minimum value is f of 7 pi over 6, which is, what is the function again? Cosine x. So this is cosine 7 pi over 6. You know what? I end up writing it very, very small later on. Let me bring this down a little bit. So this is cosine 7 pi over 6 over 2 plus sine 7 pi over 6. Cosine 7 pi over 6, that's negative radical 3 over 2 plus, that's quadrant 3, right? And then sine 7 pi over 6 is negative 1/2 times 2 over 2, that will give me negative radical 3 over 4 minus 1. So negative radical 3 over 3. Okay, so that's the local minimum value. Local minimum value. The coordinate, however, is 7 pi over 6 negative radical 3 over 3. I honestly don't know what is that approximately. Okay, well, we can use calculator for that later on. Okay, how about local max? Local max, as we see here, local max is, you see that the slope here is positive and then becomes negative. Okay, at the transition at 11 pi over 6, right? So that will be local max at 11 pi over 6. At x equals 11 pi over 6. So f of 11 pi over 6 is cosine 11 pi over 6 over 2 plus sine 11 pi over 6. This is positive radical 3 over 2 over 2 minus 1/2. Multiply the top and the bottom by 2. That will be radical 3 over 4 minus 1. Oh, that's radical 3 over 3. Okay, so from there we see local max is radical 3 over 3 with the coordinates 11 pi over 6 radical 3 over 3. Okay, that's very, very small, huh? Let's come back here. We know that it will be local minimum at 7 pi over 6. So let's say it's here. And local maximum at here, 11 pi over 6. So seems like the graph later on will be going down here, and then later on going to go up here, and then at some point there it goes down again. Okay, so this is 1/2 is not the absolute maximum. Yeah, the absolute maximum later on you will see is that radical 3 over 3. Okay, maybe my graph is not correct though. I'm not sure about the concavity yet at this point. That's when we do the second derivative test. But as for the slope being positive or negative, we know that it is going down here, and then later on it goes up here and then go down again. Okay, this is 7 pi over 6 here. Let me enlarge. This is 7 pi over 6, and somewhere here 11 pi over 6, it reached the maximum. Okay, I will regraph that later on with a better one. So far this is just a sketch. Okay, now the third stage, the second derivative. Okay, what did I use earlier? Second derivative. Our first derivative was, I don't remember, it's negative of I know it has something to do with negative. Where's that? Negative of 1 plus 2 sine x. 1 plus 2 sine x over 2 plus sine x being squared. So the second derivative will be negative of the derivative of the numerator times 2 plus sine x being squared minus, let me move this to the left, minus the numerator times the derivative of the denominator over the square of the denominator. Let me make it to the power of 4 right away, which is equal to, oh, I have negative at the front. This is 2 cosine x times 2 plus sine x being squared minus 1 plus 2 sine x times 2 times 2 plus sine x times the derivative of 2 plus sine x is cosine x over 2 plus sine x to the power of 4. On the numerator, we have common factor 2 plus sine x, right? Actually, let's see. I have common factor 2. Let me play with my color. I color coded. I have common factor 2 with cosine. So I take 2 cosine x as a common factor, the yellow one. Okay, and then I also have common factor 2 plus sine x, right? So 2 plus sine x. So in the first term, I have another 2 plus sine x not accounted for. And then in the second term, I have 1 plus 2 sine x not accounted for. I hope I'm okay so far. Oh, sine 2 plus sine x on the top, one of the cancel with one of the 2 plus sine x at the bottom. Okay, so let me do the cancellation at the same time. 2 cosine x, the yellow part, and then 2 plus sine x at the bottom, now to the power of 3. Inside the bracket now, 2 minus 1 is 1. Sine x minus 2, sine x is minus sine x. Okay, now then from there we see f double prime x is equal to 0 when cosine x equals to 0 or sine x equals to 1. Where sine x equals to 1 means x equals to pi over 2. Well, if I include the period, that will be plus 2 pi k, right? Cosine x equals to 0 when x equals to pi over 2 or 3 pi over 2. Now f double prime x is undefined when 2 plus sine x equals to 0, but we have seen that earlier. That implies sine x equals to negative 2, which is not applied, right? Now with that then we can sketch the sine graph on the second derivative. Let me just do it here. Okay, from 0 to 2 pi, let me give myself some big space. Okay, and the criticals are pi over 2, which is, let's say this is pi is here, so pi over 2 and 3 pi over 2. Okay, that's the second derivative becomes 0 or undefined. Right, and then we do testing point again. We do testing point. So let's say I do testing point. Oh, I use pi. So f double prime pi equals to negative of 2 cosine pi times 1 minus sine pi over 2 plus sine pi being cubed. This is negative, cosine pi is negative 1, sine pi is 0. This is 1 cube. So this is positive 2. Which means, so this is positive here. When you check 0, for example, when when you check x equals to 0, f double prime at 0, that will be negative 2, cosine 0 is 1. So that's negative 2, right? So it's negative second derivative here. You will see this is also negative second derivative. So the function fx is concave up on the interval of pi over 2 to 3 pi over 2, concave down on the interval from 0 to pi over 2 union 3 pi over 2 to 2 pi. Okay, from there we also see that part H, the inflection points at x equals to pi over 2 and x equals to 3 pi over 2. So what is the value of the function there? So that we get the coordinate, right? So the value of the function at pi over 2 is, what is the function again? Cosine x over 2 plus sine x, right? Cosine x over 2 plus sine x. Cosine pi over 2, oh, that's 0 already. Oh, that's 0. Okay, likewise, the value at 3 pi over 2, the cosine 3 pi over 2 is also 0. Okay, so the inflection points are pi over 2 comma 0 and 3 pi over 2 comma 0. All of these in the first period 0 to 2 pi. Now let's sketch the graph. Okay, let's sketch the graph. This is at 0 here. Let's say this is 2 pi. Okay, so pi is here. Pi over 2 is here. 3 pi over 2 is here. I do approximation. Okay, and then the y-intercept, as I remember, 0, 1 half. Yeah, 0, 1 half. The x-intercept is pi over 2, 0 and 3 pi. Oh, okay. Okay. So this is, let's say this is 1 half. Okay. and we have x-intercept here and here, the change of concavity, right, the point of inflections. But then we have local minimum somewhere here, 7 pi over 6, so approximately here, 7 pi over 6, and at 11 pi over 6, where we get negative radical 3 over 3. I don't know what's the value though. You can just use your calculator to check. Okay, approximately like this. So I think the graph will be, oh, hold on. It's concave down between 0 to pi over 2. So the graph will be concave down here. The slope is down, but concave down also there. And then here it's concave up. And then from here, concave down. Approximately like that. Okay. The way I graph it may not be drawn to scale. Okay. So that's approximately what it looks like. Now, due to the period, then let me copy paste this red one here. And then later on, the graph looks like this. I know it's not nice. It's not nice. It's so not nice. I apologize. Yeah. And then, yeah, basically you continue going further to the right and to the left. Okay. Well, anyway, that's what happened in one period. Okay. I know my graph is not nice. You know what? Let me compute. What is radical 3 over 3? What is radical 3 over 3? I don't remember. 1 over radical 3 is what? Let me wait. 1, I'm using my calculator right now. 1 over radical 3 is around 0.57. So let's say 0.6. So, oops, I'm sorry. So it's actually somewhere around here. Let me erase this. Slightly more than 0.5. Slightly more than 0.5. Okay, so this is 11 pi over 6 comma radical 3 over 3, and this is 7 pi over 6 comma negative radical 3 over 3. Okay. Oh, by the way, from here we also see the absolute and the absolute maximum and absolute minimum are radical 3 over 3 and negative radical 3 over 3 respectively. Okay, now let's take a look again on this from the beginning. Domain, intercepts, symmetry, asymptotes. That's our sketch earlier, right? Not perfect, but at least we have some feeling, oh, these are where the points happens. Okay, and then when we do first derivative and find the critical points, we see where the function increasing, decreasing by observing the sign graph of the first derivatives. And from there, we're also able to see local maximum, local minimum. And due to the fact that this function is periodical, this local max, local min turns out to be the absolute max, absolute minimum also. Okay, and then when we do second derivative and find where it becomes 0 or undefined, then we construct the sign graph on f double prime. From there, we observe where the function concave up, concave down. Okay? So if I really put together those sign graph here, okay, just to help us imagine that the f prime x is positive and negative at 7 pi over 2, those are the critical, over 6, I'm sorry, 11 pi over 6, those are the zeros, but then it's positive, it's, I'm sorry, it's negative here, positive here, negative here. which means the function is decreasing and then increasing and then decreasing. Now, when we look at the second derivative, we found out that it has, you know what, when we do the second derivative, let me do it here, between 0 and 2 pi, between 0 and 2 pi, we found that it is concave down here to pi over 2 and then concave up from pi over 2 to 3 pi over 2. And then concave down again here. Okay, so we can update our graph now that here not only it's going down but it also concave down. Okay, between pi over 2 to 7 pi over 6, it's the slope is negative but concave up. And then between 7 pi over 6 to 3 pi over 2, the slope is positive, right? The slope is positive. And it's also concave up. Until 11 pi over 6, the slope is positive, but it concave down. Positive but concave down. And then from 11 pi over 6, the slope is negative and concave down. So you see how we catch this, right? Okay, I think one of the key steps is really like from the first derivative and second derivative, you section it further on where the critical numbers for both and see how they behave. Okay, I hope this helps though. Okay, again, don't forget my emphasis that I only did from 0 to 2 pi, but because of the period, this pattern actually repeats infinitely far to the right and also infinitely far to the left. Okay, that's the graph, approximately, the sketch of the graph. Okay, that's for now.